Well, welcome back, everybody. We're going to start the day by going over answers to your 3.2 assignment from last Tuesday. So here I have some listed. I'll go over a couple examples that you might have questions on. For numbers 2 through 6, you were asked to tell whether the function was exponential growth or exponential decay, and then find the constant percentage rate of growth or decay. So for number 2, it was an exponential growth function. The function was P of t equals 4.3 times 1.018 raised to the t. Obviously, that's exponential growth because the base is larger than 1. Just a little review. Number 4 was exponential decay because that function said f of x equals 5607 times 0.9968 raised to the x. And again, that base there is less than 1, so that made it decay. It's just a little review of what we did last week. And then the second part of that question was find the constant percentage rate of growth or decay. Well, remember, it's how far away from 1 you are as a percent. That's the percent rate of growth or decay. So in example 2, 1.018, well, that's 1.8% above 100. So, or you could think of it as it's 0.018 added to 1, 0.018 is 1.8%. And then here you would take 1 minus 0.9968, and that would give you that 0.32%, or 0.0032. Write that as a percent, it's 0.32%. For 8 through 18, the instructions were determine the exponential function that satisfies the given condition. So you can look over some of these answers here. Number 8, you were told the initial value was 52. So that's that first number that you multiply by. It's increasing at a rate of 2.3% per day. So that tells you would add 0.023 to 1, getting this as your exponential function. Kind of go through that same process for each of these. (10, 12, 14), they were pretty basic. Then you got to 16, which might have caused you a little bit of trouble or questioning. Number 16, you set it up the same way. They told you the initial population, so that probably wasn't an issue. But then what might have been tricky to you was that it's doubling every 7.5 hours. Well, since it's doubling, it's increasing by 100%, which would give you a base of 1 plus 1, which is 2. And then when it says doubling every 7.5 hours, well, what you can do is you can write x in terms of hours instead of days. That's not an issue. We went over an example like that the other day. But then when they tell you it doubles every 7.5 hours, then you can take x divided by 7.5 as your exponent. A way that you can think about this for it to make sense is x is going to be your number of hours. It doubles every 7.5 hours. So once x equals 7.5, then it doubles. So by taking x divided by 7.5, it's not going to double until you get to 7.5. So then every 7.5 hours that elapse will give you another integer, if you will, in the exponent, which allows it to double and double and double every 7.5 hours. And that's why it works that way. Number 18, what might have been tricky for that is, again, not the initial value, because that's, they tell you the initial mass is 17 grams, so that shouldn't have been an issue. But then it says it halving every 32 hours. Well, halving, that's the same as cutting in half or losing 50%. So what's tricky here is they put a negative here for your answer. You probably would have done 17 times 1/2. And then just like number 16, you might have had trouble thinking of the exponent or writing that correctly. But again, if x is in hours, it would be x divided by 32 because it halves every 32 hours. And this is the answer I would expect from you. But I mean, you know the math involved for why this negative is the same answer. 2 to a negative is the same as 1 over 2 to the same positive. So either of those answers would have been just fine. Numbers 20 and 22, basically, they're the problems where you're given the initial value and you're given another point and you plug in those points to solve for those equations. So the answers are shown here. It's just like section 3.1 when we did that. You can tell for number 20 here, I'll just mention a couple things, I guess. Number 20, the initial value is negative 5.8. This comes from plugging in when x is 1, g of x or y is negative 4.64, and then you can solve for 1. Excuse me. As we mentioned, it's real easy to do that when x is 1. Well, anything raised to the 1 is whatever the base is, so then you have simple arithmetic to solve your problem from there. And then for number 22, same type of thing, only you're not given when x is 1, you're given when it's 4. So you'll have a fourth root involved, just like on 3.1. (24) through 28 were kind of your challenge problems. And by challenge, I just mean I didn't spell out how to do them to you. But you're going to use this model, your logistic model here, where that C value is going to be your limit to growth, and A is your initial, well, you're going to get A by knowing your initial value. Let's just go through 24 here. You're told that C is 60 because you're told in number 24 that your limit to growth is 60. So right away you know it. You're going to plug in 60 for C. You always have a 1 here, so that's not changed. Now you're also told that your initial value is 12. Well, your initial value means that you would plug in a zero here for x. Well, anything raised to the 0 is 1. So if your initial value as told is 12, well then you're simply solving 60 divided by 1 plus a equals 12. Whoa. So then it just boils down to cross multiplying, and actually you just do this in your head. 60 divided by 12 is 5. Well, 1 plus what equals 5? 4. So your A value would be 4. So now you've got everything except for B, but you are also given that the logistic function is going to pass through the point 124. So since we already know A is 4, we already know C is 60, we're plugging everything in, including now, since we know it passes through the point 1, 24, we plug those in. So we plug in a 1, we plug in the 60 we already knew, plug in the 4 we already knew, we plug in the y value of 24, and now we just solve for b. And once you're done with that, you have your equation. And you do that same type of thing for 26 and 28. So you might need to pause for students to check this. Oh, missed 28 here. Oh, you weren't assigned 28. I guess for just for 26 then. For number 30, just a word problem where you're setting up the problem. You're told the 2000 population in Las Vegas is 478,000 and is increasing at a rate of 6.2% each year. So your initial values, that 478,000, it's increasing at 6.28%. That's going to give you a base of 1.0628 raised to the t. Now you're asked at that rate, when will the population be 1 million? Set that equal to 1 million and solve. Solve by whichever means you feel you can do that, whether it be using logarithms or graphing the functions and seeing where they intersect. Similarly, with number 33, you're looking at radioactive decay. Again, you're talking about the half-life. The half-life of a certain radioactive substance is 14 days. Well, and then you're given an initial value of 6.6 grams. And that should tell you half-life means that your base is 1/2. Initial value is 6.6, and the half-life is 14 days. So so that tells me I could take t over 14 if t is the time in days, because once the number of days equals 14, that's when I get to the half-life. That's your equation, which you're asked to set up. And then when will there be less than 1 gram remaining? Well, this is just set that equal to 1, or type in this equation and type in y equals 1 and find the intersection. Your assignment for today is to work on the second part of this section. You're going to do numbers 34, 37, 39 through 46, and 51 through 56. Also, make sure that you take notes on 3.3. I'll check those right away at the beginning of class tomorrow. You're going to be talking about logarithmic functions and their graphs. So it'll be a review of what we have talked about already. But make sure you take good notes, read through the example problems, maybe write a couple of the example problems down so that you can start into this assignment tomorrow after we go over a couple of other things.